Welcome to Study Loop.
Hey everyone, this is question number 11 from chapter 21. In this problem, we're given that we have one proton fixed and another proton that's released from rest 2.5 millimeters away. We're asked to find the initial acceleration of the proton after release, and then we're asked to sketch the acceleration time graphs and velocity time graphs of the released proton. So let's start with part A. We're asked to find the initial acceleration of the proton. So with acceleration, and we're dealing with charges and force, so we should think of F equals ma, Newton's second law, and we are looking for acceleration. We know the mass of a proton, and then all we're left with is F, and F with charges should get you thinking of Coulomb's law, F equals K Q1 Q2 over R squared. So we can start this problem by solving for F, and then we can move to solving for acceleration. So F equals K. We can go ahead and write out these values. F equals K is Coulomb's constant, 9 times 10 to the 9th Newton meters squared per Coulomb squared. And then we have Q1 and Q2. The charges on two protons are obviously going to be the same. So that is 1.6 times 10 to the minus 19th coulombs. Times 10 to the minus 19th. Let me write that 19 a little bit better for you. And we have two of those, so it's going to be squared. And then we divide that by r squared, our radius, which is 2.5 millimeters. We have to change that to meters. So that's going to be 2.5 times 10 to the minus 3 meters. And that is squared for r squared. And that's going to give us, if you plug this into your calculator, that will give you a force of 3.69 times 10 to the minus 23rd newtons. And now we move on to F equals ma. Sorry about that. So now we have F equals ma. We're solving for acceleration. We rearrange A equals F over mass. Plug in our numbers. Force we just solved for, 3.69 times 10 to the minus 23. Newtons divided by mass of a proton, which is 1.673 times 10 to the minus 27 kilograms. And when you plug that into your calculator, you get an acceleration equal to 2.21 times 10 to the 4th meters per second squared. So that's our acceleration of the proton when it's released from rest. So now we go into drawing graphs. So start with acceleration time graph. This is I'll rewrite it, A on the y-axis, T on the x-axis. So when you look at Coulomb's equation, F equals KQQ over R squared, if you divide K over to the opposite side, you're left with a ratio of 1 over R squared, K and Q over the other side. And we have this relationship, A equals F over M. So we can relate those two, A equals F over M, proportional to 1 over R squared. Meaning that the further away that you get, the smaller the acceleration is going to get, and you're squaring that, so it's going to be parabolic. So we start with this high acceleration, and we're going to slowly decrease acceleration eventually. So now if we look at velocity, acceleration is slowly decreasing, but our velocity is increasing. So velocity is going to eventually increase and even, I guess, kind of plane out to a certain asymptote once this acceleration eventually equals 0, when they're far enough away, infinitely far enough away, where the two protons aren't affecting each other anymore. So those are your acceleration and velocity graphs, and that is your acceleration for the released proton.